Hello, I'm Rebecca Lewington. Welcome to our podcast. I'm very pleased to have convinced Kel Guerin, co-founder and chief innovation officer of Ready Robotics, to join me today in the Micron virtual podcast bunker. Kel, thanks so much for joining me.
It's my pleasure. Thank you so much for having me.
You're very welcome. Industrial robotics is a different world. Fragmented, proprietary, and about as far from the standards-based IT world most of us inhabit as you can get. Ready Robotics has just announced ForgeOS 5, which is an open platform designed to fix that, making it quick and easy to develop automation apps across all major robot brands. They happen to be partially funded by Micron Ventures, but that's not why we're here. We're here because Micron is helping Ready Robotics to make the next big leap forward, using advanced AI to help robots to learn for themselves. So before we get into that, first, Kel, tell us a bit about yourself. What's your background and what's the mission of Ready Robotics?
Sure. So I've been in the robotics space for about 10 years. I've worked on robots in all sorts of different environments, from space systems, mining, uh, systems for medical applications and surgery, and industrial processes. And the work at Ready really came out of work that I was doing at my PhD, thinking about how people interact with robots, because all of those systems sound really cool and they also sound really difficult. Like, it sounds difficult to put a robot on the moon, but it's actually been done, and it was done back in the 60s, right? It's still difficult, though, for a person to interact with that robot. And all of the different robots that I've seen, the people part of the equation was usually the most challenging part, is how the person, whether it's the surgeon or the miner or the worker in the industrial setting, actually interacts with the robot. And so Ready Robotics was designed to really commercialize some of the technology that we had built in terms of how to get a everyday person at a factory to be able to program any robot using a very easy piece of software, rather than the sort of esoteric programming languages that exist today.
It's not a thing most of us really think about, I don't think. So how do people train a robot today? I haven't trained a robot this millennium, but back then it was a very manual process to guide the robot and tweak the program until it actually worked. What's different now?
So not a lot. In fact, if you were programming maybe in the late 90s, the interfaces that you used back then are virtually unchanged today for most robots. There's a lot of reasons for that, but a lot of it just comes down to robot companies are really focused on the hardware and not necessarily on the user experience. So you're right, it is a lot of learning how to use a very specific programming language for a specific robot brand, and then using and writing lines of code in that programming language to actually make the robot do the things that it needs to do, visit the points that it needs to visit.
So you want to move things forward a bit, I think. When we talked about this before, you said you were going to try and change the way a robot learns. Instead of teaching a robot, you want the robot to learn. Can you say some things about that?
That's exactly right. So a lot of what we're talking about in the manufacturing space are things that are being done over and over again, right? Let's say I'm a factory and I have 50 machine tending systems, right? So I have 50 CNC lathes, and each one needs a robot in front of it putting parts in and out of it, right? Traditionally, even with our software, you'd have to program every single one of those robots. Now you can copy and paste, and maybe one program is very similar to the next, and so you can take a good portion of it and translate it over to the next machine, but you're still doing a lot of work for each of those 50 machines. Imagine if you program 10 of those machines, or 5, and by the end of that time period, since the machine, the robot and the algorithm knows that you're doing lathe tending, right? CNC lathe tending. It goes, hey, I kind of know how to do this, right? All you really need to specify for me now, because I understand what you're doing, is maybe you just give me a couple of points and I'm going to take care of the rest. So you can imagine a piece of software like that that learns over time how to do this task that you're teaching it to do, so that the next time you deploy a robot under those same circumstances, the system is sitting there going, hey, I know how to do most of this. You just need to give me a couple of pieces of information, rather than programming the entire thing step by step.
So that sounds more like the way a child learns.
That's exactly right. And there's a lot of similarities in sort of the state-of-the-art robotics research when we think about how a child learns, specifically like a toddler from like 12 to 18 months versus an industrial robot. And the goal there is that the way a child learns is they learn by interacting with their environment, right? They move things around and they sort of explore and they learn how to build up sort of specific skills. Like I know how to lift something, I know how to push something, and I know where it's going to go when I push it. And then eventually they can sort of abstract those skills together into goal-driven tasks, right? Hey, if I want my juice, I need to pull the cup of juice towards me and then lift it up to my mouth, right? Like that sort of as a set of skills that they've learned to do that. Well, we can teach a robot in a very similar way. By sort of taking each skill that the robot does, grabbing, lifting, moving, transporting, and start to put those together into goal-driven tasks. Take my part and put it in the lathe and then take it out once it's done, right? The issue with that is that a toddler has years to learn how to do those tasks, right? And we do not have years for an industrial robot to learn how to do the thing it needs to do. We have, any time that the robot's not sitting there producing parts is time that, money that we're spending essentially on our task. And so finding ways to accelerate that learning, we kind of know how we want these systems to learn, but we need to learn faster than letting the robot just play with its toys and then eventually getting back to us once it's done. We need to be able to learn faster than that.
It's quite easy to say we want the robot to do this, we want the robot to learn this way, but you described it as not a solved problem. What's the central challenge here?
Right. So it's this idea of the robot getting better over time at something. And there's sort of a couple of different methods that are core to this work. One is reinforcement learning, where you're essentially showing the robot the right way to do something, right? Instead of letting the robot explore like a toddler with its toys, right? And eventually it sort of figures things out. You're giving a very specific example to the robot, like the first 5 times that you program the robot to put parts into a lathe, right? You're giving it very specific targeted demonstrations, which means then that it can now go and do its learning, but you've sort of seeded that learning with how it's already supposed to be done. And so the robot is much more quickly able to learn in that context. The other thing is when you have scale, when you have more than one robot learning these same tasks at the same time, not the same identical task, but let's take those first 5 robots. Even if the robots are not exactly the same, maybe they're different robot brands, maybe they're different shapes, right? Maybe the machines are slightly different and the task is slightly different, but they're still tending a lathe, right? They're still picking up objects, putting it into a constrained space, pulling it out when they're done. The task is the same, right? I can say they're all doing lathe tending, which means now you can employ another learning strategy, which is called transfer learning, which is basically if you have multiple robots, even if they're different, learning the same task, the same high-level task, even though the parameters of the task might be different, you can now transfer that knowledge from one of those robots to another. And so you can sort of build this smarter, centralized model for how this task is done that's built from the experience of all of these robots that are doing this task simultaneously. Again, with the idea of speeding up this task, right? So as the robots are actually performing the task in production, right? They're making parts. They're not costing you money. They're making you money. They're actually performing that learning and sharing that knowledge with one another so that, again, once you get to the 6th or 7th or 8th lathe, the model is good enough now that those robots have experienced that task enough that they can say, hey, I get the basics of this. I know how to move. You really just need to tell me what and where.
And ForgeOS is the thing that means you get to multiply the training set, and then you use the training set everywhere without having. So ForgeOS solves the data problem.
Yeah, exactly. So when you see, and you saw this in research quite a bit. So for instance, Google built a very large test bed for doing reinforcement learning. And they had, dozens of robots in this lab that were all identical, and they had sort of had to build up this sort of engine to train this specific task with all these different robots, and the robots all had to be the same. The data coming out of them had to be the same. It took a lot of effort to do that, right? Well, because we've built ForgeOS with the notion that it provides a sort of common interface to all of these different robots, then let's say you're at your factory, you've got those 6 robots doing lathe tending, they're all different. But if they're all running Forge, then they're all kind of the same, right? The data coming out of them is the same. You have additional data coming from the fact that a person programmed them, so there's all that task knowledge that comes with. So you don't have to sort of contrive a sort of research system in order to learn this information. The robots that are on the factory floor, even though they may be heterogeneous, are all giving you the same data, and you're able to learn in the same way and perform that transfer learning in a much easier fashion because the data is already the same. You might have to change things because the robots are shaped differently and things like that, but the data coming out is very similar. And so again, you don't have to sort of contrive an example to learn these models. You can do it with the robots that you have in production, even if it's across different factories, right? If you look at large conglomerates, large machine tool companies that might have dozens of factories, they have lots of lathes in those factories and lots of robots on those lathes, but it's all over the place. This still provides a common layer across all of those different robots that are learning that task so that they can learn from one another in this manner.
Very clever. So you've got the data part sorted. What's the next challenge?
So the next piece of it is really the computational piece. And that's where we've been really excited to work with Micron on this collaborative research project, because Micron has a very specific set of hardware geared to solving the computational challenges of reinforcement learning and these other algorithms I discussed. And fundamentally, we're talking about building neural networks, right? That's really the tool set that we use computationally to do reinforcement learning. Is we build a neural network that sort of encapsulates the knowledge of how to do the task, all of that step-by-step information. And that neural network takes some very intense computation in order to build. And then also, when you sort of want to ask that neural network a question, you want to say, hey, I'm at this step of the task, what's my next step? And you have to go to the neural network and perform that sort of update so that it tells you, hey, now you do this, right? That is a computationally expensive operation as well. And so Micron has built the DLA, the deep learning accelerator hardware that is designed, it's an FPGA-based system that's designed to really help with this acceleration, because the work that Micron has done to make it very easy to take a neural network and load it onto this piece of hardware that makes those type of updates very, very fast, really allows you to unlock the type of algorithms that we're talking about. The other thing that's great is that Micron's hardware works on a lot of different form factors, right? So in an embedded system, if I sort of have like a desktop PC size system, or if I'm actually offloading this type of computation to like an edge server or even the cloud, the DLA works in all those different contexts. So you can have a robot that is running Forge and have it communicating with this computational resource of the DLA to actually do these updates, no matter whether that's that card is sitting in the computer connected to the robot on the factory floor, or whether it's off in a server closet as part of a larger system, right? So it's a very scalable and flexible platform. But again, the point is that now, because we have all of this data from all these different robots, it's all the same. Because of Forge, Forge can connect with the DLA so that on board, as part of the system, you can do this learning sort of intrinsically, rather than having to send it off to a different server to run on different hardware. It can sort of live there and learn on board.
That's great. And I'm very pleased to hear that Micron was able to help you out with more than just funding, but also with expertise and actual physical stuff. That's excellent.
Exactly.
I have to ask you, what do the robot companies think of Ready Robotics? Are you a force multiplier, or are you a competitive threat of some kind, just making them a commodity?
No, it's definitely a force multiplier, because if we look at the trajectory of robots that we're on right now, a very straightforward corollary is the computer industry during the late 70s and early 80s, right? Late 70s, most computers were big server installations, expensive, took a lot of expertise, and were not used by a lot of people. Once you had a common operating system like Windows and DOS, and you had companies like Apple thinking about usability, right? Then all of a sudden computers exploded. And there weren't any computer companies that were sort of sad about that. They were all super excited about it because they were selling so many more computers, because now the everyday person could get value out of one of these systems rather than just a handful of people in some big company or a bank or something, right? So we're at sort of that same point in the robotic space today, where we're sort of in the server land of robots, lots of big robot installations at car companies and things like that, where it really takes experts to use them, and it's really only these larger installations. We're moving to a world where robots are being used everywhere, and that's because of products like Forge, where you have this common layer where all of these robots are very similar, like Windows, and you have a focus on usability with our task canvas application, so that the everyday person, just like an Apple computer in the 80s, can balance their checkbook, except with the robot, now you're programming it, right? So it democratizes the ability to use robots, which just makes more robot users out there and more demand. So when we talk to robot companies, we're not talking about like, selling 10% more robots than they're selling now. We're talking about a world where they could sell 100 times as many robots as they're selling now. And that's very exciting for the entire industry, that unlocking that type of growth that we've seen in computers. We know it's possible. We know that robots are as equally capable of devices. They just need to be unlocked in a similar way. So we've had a lot of excitement about our product.
And that is very exciting to be in at the beginning of an explosion, and to be one of the reasons why it's happening is amazing.
Exactly, yeah.
So just to finish off, Kel, what's next for you?
So we're really excited about our Forge 5.0 launch, which is on May 11th here in the next couple of weeks, where for the first time, a lot of people are going to be able to see what we've been building. Forge has been out there in the wild for almost 4 years now, but this latest version of our software is really a lot more scalable and designed to be this development platform that is really powerful for people thinking about building robot applications and machine learning applications in the industrial space. And later this year, we're going to be releasing our Forge SDK. So you'll be able to download a developer kit for actually building solutions with Forge, whether you're building software plugins or actual apps. Just like you can build apps for Android or iOS, you'll be able to build apps for Forge. And we're actually currently allowing people to sign up for that. And we'll share some information about that, so that you can actually get access to that developer kit for free for a limited time. So we're really excited over the summer to sort of be releasing slowly this developer SDK. And we're starting to see people really building incredible technology on top of Forge. And the partnership with Micron just sort of reinforces that, right? Because our whole goal is to build a tool set to the larger community where it's easy to build applications that run on any robot. And in the machine learning space, that's just as vital. There are so many people working on incredible applications that use machine learning for robotics, that there's a high barrier to actually get that out into the commercial market. And with the sort of agnostic operating system that we're building with Forge, and with the computational tooling that will be possible in partnership with Micron, we're really excited to have those developers sort of be unleashed on all of these really interesting problems in the robotics and manufacturing space.
So that's amazing, because it sounds to me like not only you're inventing the operating system for the robotic future, you've also pretty much invented the DevOps environment for it as well, all in one fell swoop. That's amazing.
Yeah, that's the idea. And it's really to, this is about empowerment, right? The people out there who are working on the factory floor every day, who aren't able to utilize robots as a tool to make themselves more efficient, right? We want to empower them with easier to use technology. There's also a huge world of developers, software developers, that understand that the manufacturing and logistics space and the robotics space is a really interesting place with really important problems that have serious consequences for the world. And they want to develop software solutions, and they want to build cool things that can help solve those challenges. And they haven't really had an easy way to do that. It's been really hard to get into that space. And Forge is designed so that even if you're not an expert in robotics, but you're a software developer, to make it easy, just like developing for smartphones wasn't easy in 2003, and now it is because somebody built it, right? We've built it so that these developers can get into the robotic space and build amazing solutions.
That's a really great note to end on. Kel, thank you so much for joining me. This has been absolutely fascinating, and I wish you the best with the launch.
Thank you so much. It's my pleasure, and it's wonderful working with Micron.